Okay, so let me welcome you to today's lecture. So last time we saw some various kinds of structured peer-to-peer overlays ranging from Khan and Pasture and Kademlia, and today we want to have a look at structured heterogeneous peer-to-peer overlay networks. And to remind you, or to give you an outlook, so there will be Globase, that's an overlay that we will have a look at. There's Adaptive Chord and Omicron. And they are all taking into account these heterogeneity of the node resources. Having a look at the classification, so where are we currently? Again, still we are in the structured peer-to-peer area, and previously we had these so-called homogeneous peer-to-peer overlays like Chord, Can, and Kademlia. They are the main point with them is that they are all nodes are somehow treated equally. So every node in Chord and Can performs the same protocol. So there's no differentiation whether one peer is stronger or less stronger. So today the heterogeneous peer-to-peer overlay networks, their main idea is that you somehow take into account the quality of the nodes, and we will see how this is done. So what is the motivation? So first of all, okay, structured peer-to-peer overlays, that they do some lookup, that's good, and they all have equal roles, equal routing table size, equal load, equal responsibility, but the world is different. So the nodes in the real world, they are different. So we have servers on one side, we have mobile nodes on the other side, they have different bandwidth, different storage space, and that should be somehow taken into account. So the goal is for these heterogeneous overlays, that's why the term heterogeneous, is to consider the difference in the nodes and to introduce different roles for different peers. And typically this is done by so-called super peers, so they have stronger responsibilities and more to do because they also have more power. The first overlay we have a look at is Globase, and it stands for Geographical Location-Based Search, and its main functionality is different than the previous one. So it's not a distributed hash table, it does not provide a key value store, but it implements a location-based area search. So it helps you to find all peers in a given zone or find the closest peer in a given zone. And this is done by a supernode-based structured overlay. It uses tree structure. We will have a look how it looks like. To give you a small example, what you can use it for. So the question is, so the locating is meaning the term to find the position where we are, and searching means what is nearby. So if I'm that user, for example, and I'm looking for Italian restaurants, then it should give me the location and the contact addresses of all Italian restaurants within a distance of 1 kilometer, for example. And these kind of location-aware services, they are coming currently. There's a trend, and so you find applications like Bebo, I think, or Four Fingers or Foursquare. Yeah, that's also location-based. So it's very highly attractive for end users and providers to really support that kind of location-aware services. So how can this be done in a peer-to-peer fashion? Just to show you a perspective how it can be done with our previous knowledge. So if we would take, for example, a structured peer-to-peer overlay like Chord, and instead of just having a random or somehow arbitrary ring in the world, we could use the ring to create a specific structure. So the ring in this case would go in so-called space-filling curves. So it goes along and fills the whole world, and every point is somehow matched to one specific point in the identifier space, and this is still one-dimensional. And we could use this kind of mapping in Chord to also do some location-based search, but as you can also see, it's very inefficient because it's a mapping to one-dimensional space, and two very close points in the two-dimensional space are quite far away in a one-dimensional space. What could be also done is one could take CAN to implement some physical mapping. So the geographical position could be also somehow related to the node's position in CAN. But CAN wasn't so performant in terms of the lookup complexity, so it still had this square root inside. There are also different solutions, like for example RecNet, which uses a binary distributed space partitioning tree, so it always divides the space in two parts. We will see how this can be done better. And one example, so how this is done, is globase.com, and the main topology and structure, how the nodes are interlinked, is through a tree structure. So what you see here is a super peer based n-array tree. That means that every node has n up to n children nodes, and we have different roles also for the peers. So as you for example can see, is there are peers in the bottom which are somehow not having any responsible peers below, and peers higher in the tree. So at least there's some differentiation to the roles. What you can also see in this graphic, and it will be also presented in more details later, is that you have a mapping of the geographical position also to the peer positions. And just to give you a rough idea, the tree that we create is every node that is representing a specific space on the world. So for example, this node is responsible for this area, and it is part of a larger area which is maintained by its father node, and this is also part of a larger area, and this is also maintained by its father node. So there's some link how to place the nodes and how to interconnect them. And the interconnections, these are the links. So you have this typical tree structure, and which is also defined by the position of the peers. But to not only have these single connections to your father node, you also have so-called interconnections, which extend the topology and help to increase the routing to make it better. Okay, so the main idea is that if you have a peer ID, it also represents where you are located in, and who your father knoten is. And according for these 3 points, you will see the next slides to get a feeling how Globase works. Okay, so first point is this n-array tree. So each superpeer is responsible for all nodes in its rectangular zone. So the responsibility in Globase is not anymore one-dimensional, but it's two-dimensional, because it's a two-dimensional world, and it is organized in the rectangular. So for example, node E, it's the superpeer of the zone of this rectangular zone, and that's the position of E. And E is also located in the zone of A. There's A, that's the point where A is located, and that's the zone. So the whole world is the zone of A. So that's why E is a son of A. Or if you take another example, H is located here somewhere in China, and it has a rectangular zone and some peers for which it is responsible for. So there you find H with the peers it is responsible for. And it is also, this rectangular zone is part of the rectangular zone of C. And that's why C is the father node of H, and C is also part of A's rectangular zone. So very simple construction principle. So peer A is called the parent of B when B's zone is inside of A's zone. So how is it then created? So this is basically the final structure of how you come up with. And first you have to set this kind of structure up. So you have to have a protocol how to create that kind of network. So you start with an empty world. And it's quite funny, just a side notice. On this kind of maps, you rarely find Antarctica. So it's somehow a continent that's missing. So we start with a first node, and because it's the first node, he's responsible for the whole space. So the whole world is now managed by A. It's not a big deal, he's only one node. So, and if further, this is the current tree structure. And every node also maintains a local load, so that's the number of peers he's responsible for. And this is somehow a progress bar that should visualize it. So it has two bounds, first a lower bound and an upper bound, and we will see how it is used. And with time, more peers join, and they contact the peers which are already in the network, and so they contact A and ask, hey, I want to join, take me as a child. Okay, A takes everybody as a child, and so its load rises. Now more and more peers join, and the load of node A rises above the upper bound, L2. Okay, and so every node has a specific upper bound. You can also put them the same, but the idea is that the upper bound is the maximum load that every node is willing to take. So this is the maximum number that of nodes that one peer is willing to be responsible for. So in this case, the upper bound has been succeeded, and that's why we create a new zone, and so we want to reduce the load. So that's why a new zone is taken out of the responsibility of A. A new responsible peer for that zone is assigned, and that could be the strongest one. And that amount of load is given to B, so that A remains with the lower bound of load. So it gives all the load which is between basically L2 and L1 to the new zone. And the tree structure evolves. So we have now a subtree with B and the nodes inside. And with time, more and more nodes join, and every time the load is succeeded at some specific super peer, he splits his area, creates through a clever mechanism, identifies the hotspots. So for example, here are more nodes, so that's why he could take, for example, a smaller rectangular space to reduce the load. And with time, this kind of tree structure evolves. Okay, so let's get some feeling for these thresholds, L1 and L2. So if you take the lower bound and the upper bound very small, so 5 and 10, and you have, for example, 1,000 peers, then you come up with the picture in the top left. So you have very many zones, and that's how it looks like after a simulation of 1,000 peers. So for example, the blue ones, they are located inside the violet ones, and here, for example, in the USA, there are quite a lot of zones. If you take large numbers, 50 and 100, for example, then you come up with only 14 zones in all. So you get the feeling how these thresholds influence the structure of the tree, and you get also a feeling that these thresholds could be also chosen, can be chosen by the peers to fit also their capacity. So if a very strong peer, he could say, okay, I take more nodes, and a smaller super peer could take less nodes. So you still can adapt to the quality of the peers. How's the PID chosen? So what is also somehow new in Globase in comparison to Core is that you put inside some further information, not just a random ID basically, but one of the main information is the GPS coordinates. That's basically your X and Y coordinates in the landscape. You have also the zone of responsibility that you can announce by giving the shape of your rectangular if you are responsible for one. And there's a random part for all the nodes which are placed on the same GPS coordinates and don't have a zone of responsibility, so that part would be 0, and so that they can be differentiated. Ah yeah, that's the same what I told. So X and Y coordinates and the zone of responsibility, so rectangular shape. Yeah. So the good point is, by having that kind of PID, you do not have to communicate to the other nodes your responsibility range, because by knowing your ID, they also know for what kind of area you are responsible, and they don't have to contact you and ask you in order to check whether some super peer is responsible for a given point. So they just look at your ID and know automatically where you are and what you're responsible for. Okay, so having this network topology in mind, now we come to the interconnections. So what are interconnections? So first of all, up to now we only presented these links between the father nodes and the children nodes that are coming somehow automatically by the responsibilities. But what you want to have is to have also some robustness, and so if, for example, a father node would crash, then you do not want to lose all of his children. So that's why you introduce these high interconnections. That means that you also establish connections to your grandfather nodes and grandfather nodes, so that you are not lost. Once your father is lost, then you can still contact some higher ranging nodes and ask for your current responsible node. You also have these wide interconnections, which are ranging to some areas which are not in your area at all. So if you're located probably in Europe, that could be somewhere in Australia, and the point is that should support the routing. So we will see at the end how routing is maintained, but just keep in mind that by having many links across the world, at the end you will find quicker the positions that you're looking for. So the higher interconnections, so that range up, that's for failure recovery, and the wide is for more efficient search. And from theoretical point of view, the idea is to extend the network and the tree to create an expander graph. That means that the diameter in the network becomes quite small, and you can reach any point quite quickly. And how do you identify to whom you should send the messages, whom you should contact? So first of all, that's like in Kademlia. So you also look at received messages, and you see who is sending the message, so you can also contact that nodes. You might also ask your neighbors about their routing table information, and you can also directly ask your father nodes, so the nodes in the tree that you are somehow linked to. Okay, so one very prominent functionality in this GLOBase, this location-based search, is the area search. And the point is to search for all peers in a defined area. And here the emphasis is on all, because you don't want only to find 50% or some, but you want to really find all nodes in that area. And that's, for example, to give you a use case, typically it is said if you, for example, would have a sensor network area and some trees and some forests, and you drop out some mobile nodes, they could automatically create this kind of peer-to-peer overlay, and so that you can find all sensors within one given range, and you could define some area what you are interested in and retrieve all the information from it. So you want to find all peers in a defined area, so that's why you give the center and the radius of that area, and of course you also give your own information into that search message, and the responsible super peer from whom you send it. So if you are one node somewhere here, so for example you are near this point, near Kamchatka in Russia, and then your responsible peer is C, so you add your own ID, you add the ID of C and the position that you are looking for, and the position that you are looking for is, for example, somewhere else in Africa, for example. And what happens then is that the super peer calculates the searched ellipse, because if you map it to the world, then you don't have any more center and radius, but you have more some stretched ellipse. And it checks next whether its own zone is intersecting. We will have an example for that. so it checks whether it's, so let's assume we are looking for a place here in Egypt, and we are starting in C. So then a C would check whether its own zone is intersecting, so it contains some of those nodes that are looked for. And if not, then it checks whether some of the interconnected nodes that you had interconnections to are intersecting with that desired area. And if not, or even if, then you still forward it to the parent node to find the whole range of peers which intersect with that area. Let's have an example. Okay. So this is node B. He's looking for something, and that's why so this node in the area of node B is addressing his search to the node B, and this is the area that is looked for. And what B does, if it wouldn't have some interconnections, just in the plain protocol, it forwards the message up to the root, which is the first one who totally involves the whole searched area. So as you can see, in this path, A is the first one, and A pushes down the request to all of the nodes who are intersecting with this area. And now all of them, I hope this is also an animation, note is not, and all of them then send back the information to the peer looking for the desired area. Another example, in this case, some node in J, so that one is looking for this area. So again, you send out your query to your super peer, and he is sending it in the worst case to the root, which then forwards it to all nodes and all super peers who are intersecting with that area. It's somehow easier if you are looking for a smaller scale. So if J would look only for some area here, which is also located in the US, then it would only consider the super peer J, and the other nodes would not be bothered. Or if if that node would contact some area here in D, then also only J and D would be somehow contacted. So I think you get a feeling of how the routing is working in Globase. Okay, so what are the to summarize characteristics? So very prominent, very important, location-based search, not the DHT, and it creates a tree structure which basically maps also the geographical position of the nodes, and introduces some responsibility rectangulars. And what you come up with is a fat tree structure. That means that strong peers are located at higher positions in the tree. And this is because you can pick, while creating a new rectangular zone, a new responsibility area, you can pick where to place it and which node to assign to it. And so you can also pick the strongest peers. In normal case, no peer is overloaded, because if it's overloaded, then it would create a new zone and it gets less load. It uses interconnections, both to stabilize, so therefore you have the high connections, and to fasten the search, that's the wide interconnections. And you perform the area search in O of log n. That's why the tree, this is because the tree has a logarithmical height, and that comes to this complexity. So what are the drawbacks? With the interconnections, that's somehow quite complex and not so natural, how and to which nodes to create them, and to make sure that you don't only map to one kind of nodes, but you have a diversification. That's not so easy. And it's also not so well done or easy, because the protocol describes how the tree grows, but it's somehow difficult to identify how to let it shrink, or which rectangular zones to relieve, and how to how to announce that you lost that rectangular zone. Although it seems somehow easy to be solved, it's still open. And the functionality, this area search, and you also have some find the local closest point, somehow that kind of location-based search. But it's still somehow limited, and there are not many applications for it. In general, what you should also take with you from this point is the heterogeneity of the nodes, so their capacities is coming into play in this part, because we have this kind of tree structure, and we can put stronger peers at higher and more prominent places in the tree. A more prominent example how the capacities of the peers can be used is with adaptive heterogeneous chord, and it tackles one main issue of chord. So if you would just think of using chord in a file sharing application, that's more general issues with chord. Yes, unidirectional lookups, but the other issue is the homogeneity. So if you use a chord in some file sharing application, and you have various kinds of nodes inside. You have very strong peers with high bandwidth, but also very weak peers with very low bandwidth. And then somehow the files or these values that you store in chord are somehow distributed by random. So you have a hash on the object ID, on the object itself, and it's creating an object ID, and you don't know what kind of peer is responsible for that object ID. It might be a strong one, might be a weak one. And you might have the problem that the requests are, and they are typically CIF distributed. Let's just jump back. So if you have the request pattern CIF distributed, that means that you have very few documents that are very popular, and very many which are not so popular. So, and if you have one very popular document and it's located on a weak node, then you see the bottleneck. So you don't have, you have a very prominent document on a very weak node, and you don't have the mapping between popular items and strong peers. So it's just popular items and some random peers which might be weak. So that's somehow addressed in the term of load balancing. And thinking of in somehow more to model this problem, so one node can be characterized. So what is the node load? It's the ID range size. That could be a load. It can be the number of objects a node is responsible for, or it can be also the traffic overhead for providing this object. So these are three types of what you could characterize as a node load. Many papers go for the ID range size, so they try to optimize that every node has the same amount of ID space. It's still not tackling the problem of very prominent objects. Some also go for the number of objects that you are responsible for. They try to optimize the distribution of the number of objects so that every one of them, every node gets the equal number of objects, although the ID range might be different. But also in this case, you might have the problem that among these, so you might have all nodes with the same number of objects, but one object is very prominent and it's located on a very weak node. And the last one, that's I think more reasonable, is to go for the traffic overhead for providing these objects. So to take as a load only the traffic, and if you have thousands of documents that you're responsible for, but they do not generate any content because any traffic because they are not interesting for the community, then it's not much load. But if you have only one single file and it's very popular and generating a lot of traffic, then it's quite a high load. So, and it should be matched to the node capacity, and node capacity could be defined by either bandwidth, sometimes also storage space that somehow also load or some capacity. But let's try to match the traffic overhead to the available bandwidth at the nodes. Yes, so how can this matching be done? So this term of load sharing and load balancing is also somehow popular in research. There are many papers trying to address it. And some address the goal of, they try to make that all of the nodes have the equal load. That's very up to my idea, that's not very clever, because you don't really want to put the same load both on the strong peers and the weak peers. But that's what they optimize for. Typically, this is also done in very theoretic papers. That's easy to create some models for. What you can also do is to match the load proportional to the node request frequency. So if there's a node who requests many files and generates many requests and load to other nodes, then he should also have a high load. Yeah, questionable. And the last one is to match the node load proportional to node capacity, to say 60% of every node's capacity should be used. And if you are weak peer, then you still have to provide 60%. It's probably a very small number. And if you're a strong peer, then it's quite more. And this is somehow more reasonable. And looking at the application, so what the user is finally interested in is the quality of service. So he's not caring whether the load is balanced or not in his application. He just wants it to have it fast. So he doesn't want to have slow transmissions due to overload. And that's why the goal of heterogeneous chord was adaptive chord was to minimize the number of overloaded peers, and with that to have also good service quality. That means all the weak peers that are overloaded should somehow get some relief. Okay, let's see the scenario and for which it was designed, and also there will be some simulation results showing that it's working in. So the scenario is, just assume this application, you have a DHT, or file sharing, for file and object storage. And typical file size is 0 to 10 megabytes, so there's a random function just creating files in that size. And that could be music files or P2P-based social networks with very big images probably. And the requests are ZIF distributed, so that you should know the ZIF distribution is that you have that kind of ranks, that the first very prominent one is taking 1/3, for example, of the requests and all that. So you have very prominent files and a lot, but very few of them, and you have very many not prominent files. And this popularity, so which file is prominent, that also changes over time. So probably Britney Spears is not popular anymore, but it will change. So, and taking into account, so what's the difference between adaptive chord and chord? So this is the original chord. So you see, you have the normal ring, you have the node IDs. All the nodes are somehow equally have the equal rights, and the most popular files and all files are somehow assigned by random. And if they are located at some weak peers, then they are overloaded. Yeah, that's bad. And now that's how adaptive heterogeneous chord works. So what you see is, first of all, you see two rings. So there's not just one ring, but there are two rings. And the first one, that's somehow very known to you. This is the original chord ring. And which is somehow ordered by the object IDs. And the second one, what you see, is another ring which is not ordered by the object IDs but by the peer capacities. So just imagine that you have on the one side normal chord ring, but in the second ring that you are also maintaining with the other nodes in the network, you don't use your node ID as identifier but your node capacity. And with that you order the nodes by their capacity. And you can also perform a lookup for a node with a given capacity. So you could also use some request to a node which has at least that and that amount of bandwidth. Okay, but I think that will be presented in the next slide. So what is just some terms that you should know. Hierarchical is a new term that's somehow introduced because that refers to the fact that we have layers of overlays. So we don't have only one overlay, but we have several ones which are using each other. Heterogeneous, that's a term that we somehow take into account the capacity of the nodes. And yeah, the main goal is to have no peer overloaded. And we will see how this network is made up. Yeah, so the main point is the hierarchical property. So we have two overlays. We have a routing overlay. That's the lower one. That's a traditional chord overlay. It's chord with object IDs, 160 bits. And what you can do is you can state a lookup request for a specific object ID and get the file, basically. But what it can also do is it has a modification. So it introduced some mirrors so that any peer can be asked to host an object. So for example, and while routing, the original responsible peer forwards request to mirror. So just assume that the peer 3485 is responsible for the node for the object ID 3000, and it doesn't want to store it anymore. So it asks another node, for example 1622, to host it as a mirror. And once a lookup is coming for the object ID 3000, then it is received by the node 3485, and the request is forwarded to the new mirror, which is then handing out the file. So what you can do is to introduce one hop in direction, so one hop more, and store the files on some more powerful nodes. And how do you find the powerful nodes that are fitting? That you do with the capacity overlay. So what you can see, that's the higher located overlay, and it's still chord, but it uses capacity values as IDs. For example, you can assume a maximum bandwidth capacity of 1 GB per second. So this is at least what is used in a simulation. If you would implement it, you could also use 100 gigabytes. That's not a big difference. And this is the maximum, and every node basically calculates its own bandwidth capacity and puts it as its ID. So yeah, this is how you come up with your capacity ID. And what is this good for? So you both maintain, so every node has a place here and a place there, so you operate both of your overlays, and this network is used to store files and to retrieve them. And in this network, if you state a lookup request, then for example you could state a lookup request for a node which has at least 1 megabyte per second bandwidth free, and then you are routed to one which is located, for example, here. It can and then you can pick this node as a new mirror for your files in the lower network. And the picked mirror can then adjust its node ID in the capacity network. So you have always basically an ordered list of the capacity of the nodes in the network, and you can directly search for specific nodes with specific capacities, which you later on use as a mirror. So very clever. And what can be observed? So this is some simulation results comparing chord and record and adaptive chord. Basically, chord and record. So we didn't have record in the lecture, but it's very similar to chord. What you should look for is the left figure is presenting the ratio of successful lookups. No, not lookups, but downloads. And just as a reminder, so you are downloading a file between 0 and 10 megabytes, and a download is marked as failed if the download speed drops below 1 kilobyte per second for a longer time. And as you can see in chord and record, so the download probability drops to the successful ratio to 70%, while in adaptive chord, after adapting and distributing the mirrors, you come up with success ratio of around 88%. So you eliminate basically the weak peers from your overlay, so you don't use them to distribute the popular content. And if you also look, that's especially shown at the overloaded peers in the right figure. So this is showing how many peers out of 1,000 are overloaded. And in record, it somehow stays the same, around 180, because the popular files are overloading them. And in record, after distributing the mirrors, the number of overloaded peers is reduced to 6%. If you look at the download duration, that's also represented, so it's shown in the left figure, and there you can see that it's much faster than Chord, and this is specifically because if you have very popular documents, they are very frequently requested, and if you put it on a very strong peer which can support all of the requests, then you have a fast transmission, and these are so you don't have any bottlenecks, and in Chord you still have the bottlenecks. And download speed that you can also see is just double or 3 times higher than in Chord. So with this small modification of introducing another overlay to make the capacities of the peers searchable, it was quite easy to address this problem of Chord of having weak peers overloaded. Okay, so what are the general benefits and drawbacks? So what is good about adaptive heterogeneous Chord is that it effectively uses the heterogeneous capacities, it takes into account what the nodes can do, and it makes the capacities of the peers searchable so that you can really use it in the application. It introduced a dedicated overlay for dedicated functionality. So that's what does this mean? So if you have a look at related work, how they try to do some load balancing, what they typically do is they try to come up with one overlay which includes all the features. But at the end it's not so practical because that overlay doesn't have that big impact, so all the effort is somehow lost. In this case, the idea of this capacity overlay can be also transferred to CAN or Pastry or Kademlia, so it's nothing special about Chord itself. It just offers you to search for a capacity of a specific peer. So it's a reusable idea. It can be practically used, so it's not just very limited in academic sense, but also at application areas is extendable. So you can, it's a general solution, and it doesn't change the properties of Chord of this reliable deterministic routing in O log n. What are the drawbacks? So, of course, no big drawback I see about this solution, just some further issues are still open. So, in Chord you still don't have the symmetrical routing, you have security attacks and the other still open problems. So, coming to the last heterogeneous and also hierarchical P2P overlay, and this is Omicron, and it stands for Organized Maintenance, Indexing, Caching and Routing for Overlay Networks. And this was invented by a Greek, so that's why also the Greek letter, Vasilios Darlagianis, and he come up with that title, and the main goal was to integrate all of the nice features that was seen in other P2P overlays. So it should be heterogeneous, so it should take into account the quality of the nodes. It should be structured, so you should be still able to address objects and retrieve them. And hierarchical aspects have also some benefits, as we will see. So the goal was to design a new P2P overlay with all the nice features integrated, and to also handle the various conflicts. So we saw heterogeneity and load balance. I'm not sure what's that kind of trade-off, but it was also the goal to identify the essential overlay rules, so how you can in general create overlays and which kind of essential roles you have that you need to fulfill. And yes, let me just see. Okay, so how does it work? Oh, just one slide before. Let me just jump back. So just the goals that were to address. So you have that overlay network in general and the IP network. And what should be done is you want to have an efficient mapping. So you want to make sure that if your two nodes in the network are somehow neighbors and connected, then you do not want to travel along the whole world in the IP network, but close contacts in overlay should also be close contacts in the IP network. Yes. What also should be considered, heterogeneity. So that means weak peers and strong peers should have different roles. And load balancing. So you want to also, take that into account. Fault tolerance if nodes fail, of course, and scalability. Okay, so how does it work? The main picture that you should have of it is that it has also different layers, 2 overlays at least. So the macroscopic view, if you look from top of it, there you have these deep routine graphs. And we know from it that it's asymptotically optimal, the diameter is optimal, average nodes distance is optimal, you have a limited number of degree, so every node has only an out degree of 2 and an in degree of 2, so it's very deterministic. But what you also saw as a drawback is that with deep routine graphs you can only have a fixed number of nodes, so you can only have magnitudes or exponents of 2. So what do? Is that one node in the deep routine graph is not one single peer, but a set of peers. So that's why we have this kind of 2 overlay levels, and that's why it's called hierarchical. So we have on the macro level the deep routine graph, and on the lower level some other kind of overlay which implement basically one node in the deep routine graph. And the idea is to have it to support all of these points, so this load balancing and scalability. So it's also easy to see that, it's also easy to see that new nodes can just join some clusters in these lower level without the need to extend the deep routine graph. So what is inside? Basically you have redundancy, because you might have different, just a wider set of nodes responsible for a specific node in the deep routine graph. You might have locality awareness, so that you can identify, because you have this fixed node degree, you know who the other clusters you have to talk to, and you can have optimized matchings, basically optimized links. What you can also have is, of course, a finer load balance, because you have a set of nodes which you can ask to complete a specific task. And there you can shift the load like with a proxy, with a web proxy. So you have different nodes that could do the same, so you can choose. And you can also have the support for scalability, so new nodes can join. And that's very practical. Okay, so another point that they introduced besides this layered architecture is the support for peer heterogeneity. So that means by knowing the capacities of the peers and the user behavior, we can try to find some roles that are matching these capacities. And here you also see here some letters, so MICR, and these are specific roles. So what you have, and what is the motivation for all of it, is they had a look at typical peer-to-peer overlays and found out, okay, there are general operations that are always occurring. So what we have is a maintaining structure, so we should have a maintainer. That's basically who keeps the structure running and checks whether the nodes are online and updates the routing tables and just makes sure that the information is consistent, so the connections are all established. Then there are the indexers, which are basically responsible for storing the data. So they are managing the index of key to value pairs, basically. So there also is the roles of indexer. Then there are caching of popular items. So if you have very popular items and you have very frequent requests for it, then it's good to have some stronger peers which handle this overhead. So there's the cacher. And finally the routers, which participate in routing and communicating with the other clusters, so with the other Debrucine nodes. So these are the 4 roles that he found very essential: maintainer, indexer, cacher, and router, with distinguished characteristics. And you can also match peers by their capacities to these roles. So for example, for cacher it would be good to have strong peers, so with high bandwidth, but they don't have to be so long online. The indexer is more crucial to be online, so or have large storage space, so that you keep the relevant information always in the network. The maintainer, that could be also some short-living nodes which just take the role to check whether somebody's online for the 5 or 10 minutes he's online. And the router, he should be probably well connected, have short delays to all other nodes in the Debrucine graph, so you could find some mapping. How is then the lookup done? So again, this is a DHT and you can use it to store a key, store a value under a specific key and to retrieve it. And in this case, the node over here is looking for a specific item term 0011. So he uses the Debrucine graph by shifting from the right a 0 to have 01, and then a new 0 is shifted to 00. It's received by the router. Then it's forwarded to the cacher to see whether he has a quick reply for it. And finally it's addressed to the indexer. Okay, some simulation results. So what they show is like that's if you read some papers, that's very typical. So they also always show it's better than the previous work. That's nothing new basically, but so it's better than Chord. Surprise, surprise. And it's also even although there are less contacts in the network, so you don't have so many fingers like in Chord, the performance is still better. One interesting point is still how do you assign the roles to the peers, and they directly address this question in their papers, and it's the main idea is to consider the peer uptime. So what you want to have is to have peers for a longer time in the network to remain, so that it can perform the roles that it's responsible for. And one observation is that if you consider the peer uptime distribution, there's some idea that peers that are already long living are less likely to fail. That's called the burn-in method. And there are also some observations and some modeling, and what came out is basically that the Pareto distribution fits most to it. I don't want to go to detail about these distributions, but to transport you the idea. And where does this burn-in point come from? And this terminology, and this is coming from the manufacturing of components. So for example, also of creating light bulbs. And this is, for example, and this can be still applied to many aspects. It's showing in this picture, for example, the probability that the light bulb is defective, and when it is noticed. So shortly after the creation of the product, if it has an error, it breaks with high probability, and if it didn't have the problem, if it survived the specific time, for example here, then it's very unlikely that it will fail in the future. And there are also measurements in the network, in the internet, which show this fact that once you have a network, a node which is already since 1 week online, and on the other hand you have a node that is only since 1 hour online, then it's much more probable that the node which is only 1 hour online leaves the network in the next hour than the probability that the node which is already since 1 week online leaves the network in 1 week in 1 hour. So failure is less probable as peers survive, and that's some main idea that can be used to decide which peers to place at important positions in the network. Okay, so we saw many structured heterogeneous peer-to-peer networks, Globase, and then introducing these also hierarchical peer-to-peer overlays like adaptive heterogeneous chord and Omicron. So there's another slide set. Yes, just take with you, so we are leaving now somehow the area of peer-to-peer overlays, but with a slight shift. So there are still peer-to-peer overlays, but these are more general aspects for peer-to-peer overlays, how they can be improved and what could be considered in general. Just for the last slide set, for the structured overlays and heterogeneous, just take with you all of these different kinds of classifications between unstructured and structured, heterogeneous and homogeneous, flat and hierarchical, and what are the characteristics of them and which peer-to-peer overlays exist there. Okay, let's have a look at the improvements of peer-to-peer overlays. What we will have a look at is how caching can be used to improve. This one is nicer. That's a more colorful picture. So we have a look at caching. We will have a look at underlay awareness, what this means. NAT traversal, so that what's the problem and issue and possible solutions for the net address translation is. Anonymity we are not addressing, but small world graphs and power law networks, and also no network coding, so strange. Okay, so let's start with the caching. Caching, that's a term that you probably should know. So the idea is, when we have a query distribution, the popularity of the content is coming into play. So we might have documents which are much more popular. So there we have the ZIF distribution with very few nodes, very few objects, very popular, very many not popular. And the idea is, if we have this non-uniform distribution, so if we have their variance, and the stronger the variance is, the better for caching. And what caching does is basically is to reuse the information about the queries that we already answered. So if there's, for example, a query for a popular object, it can be assumed that also later it will be popular, so the answer for it could be cached, and some quicker deliveries and some quicker replies are possible. For file sharing distribution, that's the cases we have non-uniform request distribution, and the requests are ZIF or log normal distributed. Yes, how can they take advantage? Okay. The main idea is presented in this picture, so just imagine chord, and so you also see why chord is so popular, because every time there's an example with some P2P overlays, they try to refer to it. So just imagine chord, and what we can reuse as an information. So in this is, for example, the routing information, and in this case, in the lower left picture, the green node started the query for some document on the red node, and the query went along S1 and S2, and it was received by the red node, and so it was answered. What could be done if the content is very popular, the red one, is that the answer is not answered in the first instance to the querying node, but to some of the nodes on the way back. And the next time somebody is looking for the document, the steps are saved, so you don't need to do it, because one of the nodes on the way knows the position of the desired content. And in this picture you have, for example, the cache by the querying node in the first instance, and in the second in this node. So you, by introducing this kind of caching, you could save some hops in the routing. So what you need to do is to modify the routing procedure. Also need to identify popular queries, so you need to know for which objects you want to do this, and then to somehow cache them. Okay, does it scale? So what kind of problems might occur? So there might be some problem with the scalability. So there are always some queries traversing the network, and you don't know which are relevant. But because you only have a small cache size, it's not anymore the problem that it might expand and explode probably your cache, but you just have to decide which items and which objects to cache. And it's also not a big issue because you only have small number of additional messages. So in the example before, you saw that there was only one additional hop in the reply back that was introduced. It can be also incrementally deployed. So what is good about it, you don't have to change the whole network, but it's sufficient if only, let's say, 10% of the nodes introduce this change. And both the original and the enhanced peers can coexist, and there's still an improvement. Okay, what problem that might occur is how long the cached information is valid. So you don't have any problems if the information doesn't change, if it's just a pointer. But if it's dying, if the content is somehow changed, then you have to make sure that it's not so long living that you cannot refresh it. However, so the simplest method is to just wait until a peer goes offline, and then its cache is deleted, and you can distribute a new one. How does the cache structure look like? So there you could have a key, an expiration date, when it should be deleted, this cache entry, the frequency, how often it has been observed, the window reset, when it has been resetted last time, then the indices where it's pointing to, pending queries, that's what's currently going on, and the marked whether it should be deleted soon or not. One typical example to fill the cache is by using the least frequently used replacement strategy. That means if a new content arrives, then you just drop that one that has been least frequently used. So if you have k entries, then you drop the last one basically with the less requests. Okay, so what you also need is you need to be able to put it in a cache, so fill cache and get cache. So these three methods are sufficient to implement the cache. Some experiments with it in court also, and also 1,000 nodes, I think, where that are presented in this picture. So here you have experiment A and B. In experiment A, you put some content in the cache if it occurred 5 times, and you have a cache size of 80, and you reset it after 200 seconds. And experiment B, you only wait to have it 3 times occurred to put it in the cache to mark it as somehow popular. You have a bigger cache size and a smaller frequency counter reset. And what is just presented in it is that it's still, somehow, showing that the caches are still very frequently used. So on the left side, on the y-axis, you see the percentage of core routing communication costs, and on the x-axis, you see the parameter for the expiration timeout. So that means when the entries of the caches are deleted. And if you delete them only after quite a large amount of time, after 1,600 seconds, then by having a larger cache size, 50% of the routing communication costs are only needed in comparison to the original code. So you save at least somehow the half of the traffic. What this picture shows is that here's the in blue the original code, and the right the enhanced code. And just what the point is, on the y-axis is the query replies of the cached enhanced code, and the query replies of the original code network. Just in terms of how many replies have been sent, and in this picture the whole number is somehow pushed down, so you have shorter and fewer replies because the caches are used. Okay, just a very short and brief overview on caching in DHTs. So what it might bring you is it might reduce the routing cost. It can be incrementally deployed, so you don't need to change all of the peers, but only a few of them. You don't have an additional overlay network, no real big implementation effort with that. You can implement it in the overlay itself without having out of band, so you don't need further protocols. And the costs are basically just an additional delay. So if you introduce this additional reply message where you store, where you announce the hops in between, so to store some caching information, so you introduce another hop, and that's why you also have a delay, but it's not so big and it's quite simple. However, one big issue, and that's really some issue, is the consistency in case of updates or deletes. So if you change the content and the data that you have cached, then you didn't change the caches, and you cannot also find these caches. So they are somewhere and you don't have information about where they are, and so you have still old content in the network, and that's sometimes dangerous. Also, some additional storage space is required, but it's probably not so big. Yeah, and the simulation showed that you can reduce the workload, so up to 50% of the traffic overhead can be saved, and the workload distribution is more balanced, so you have less peers which are responsible for too many answers, so you don't have in this area with a very high number of replies there, you don't have any peers anymore, which you had in that other graphic. So they are all responsible and replying to less nodes, so they all have less load. Okay, so this some words to caching. Next, I want to tell some words on the underlay-aware peer-to-peer topology. So just to give you an idea and why this is relevant, and in fact this is very relevant nowadays, and because this is where the industry focus is currently on. The idea is, okay, you have an application, we have an overlay, and we have an underlay. So what is the underlay? So the underlay is basically the whole network, the internet below, and what we want to do is to somehow also consider the underlay, the internet below, and its structure in our design. So we want to use the network topology and state, we want to use the locality, bandwidth, latency, jitter, network address translation, and not only to have the upwards information, but also the downwards information. So what we want to have is also to give information to the ISP, to the internet service provider, what kind of flows are currently established, and to help both the ISP service provider to better operate, but also the peer-to-peer overlay. And why is that? So just again, the underlay, very general. It's the summary of all what is below, so physical, medium access, and network transport layers. And why it is relevant is that the internet service providers and their connections to each other are getting more and more relevant for the P2P overlay, and both in terms of latency, geolocation, and what they can offer, but also in terms of how they are structured. So if you are a typical customer in a peer-to-peer network, you are connected to your local ISP. That's, for example, Vodafone or whatever. And then you have this international transit ISPs. And one point is that peer-to-peer applications were generating a very large amount of traffic, so up to 60-80% in the internet. And these ISPs were quite unhappy about it. So what they wanted to do is to try to block peer-to-peer traffic. There are also some works trying to identify what's peer-to-peer traffic and to give it a very bad quality. So to have this prioritization, but it is somehow colliding with the network neutrality. And they were having a big motivation to really cut down the peer-to-peer traffic. And the idea was, let's try to not make them our enemies, but to make them our friends. And if we could cooperate, we both can benefit. So the idea is so that they give us some information, we give us them some information, and we both can live together. Yes. So that's summarized also in the sentence. What we want to do is to be ISP location aware or ISP friendly, and that means the ISP, the internet service provider, is defined through to whom we are connected, and what we want to do is to reduce the ISP traffic costs caused by peer-to-peer traffic. So they were really complaining about peer-to-peer traffic going around the world, although the content, mainly in file sharing aspects, was also located in their own networks. So what the main goal is to basically, if the file is also available in the same ISP's network, let's try to download it from there. And we do not want to leave the ISP, internet service provider's domain, so that he doesn't have further costs. What can also be a goal in this underlay awareness, to be latency aware. So because the peers are connected with different bandwidth and capacities at different points of the world, of course, between two nodes there are different latencies and delays if sending a message. So what could be done is to choose nodes which have a lower latency, and that could be useful to have very quick connections and very quick requests and queries, because the messages do not traverse and they don't have to be transferred so wide over the world. What can be also optimized for in this underlay awareness is geolocation awareness. That's the idea is, okay, when somebody is geographically close, let's also try to map the overlay according to it, so that we can have some further location-based services. And sometimes this also makes sense in file sharing, because if you think of what kind of movies, for example, somebody is downloading, it's highly probable that people from Germany are also downloading German movies, and people from Poland are also downloading Polish movies. So it's geolocation awareness is also useful. And finally, what can be also underlay awareness to go for the peer resources, but it's somehow more difficult to estimate. Okay, the most prominent one basically is this ISP location awareness, because they were really complaining about that they do not want to have these links used. So for using these links, they have to pay money basically, although there might be also some agreements that they both don't have to pay money, but at the end it's very it's not good for them to use these links, so they wanted to reduce it. And yeah, that's the goal to optimize for. So that's just the description. So you have the local ISPs, and it's also tree structure, and transit ISPs operate on a global plane and connect all these lower set ISPs. So what can be done is, for example, if you think of file sharing, that's the easiest. Previously, if you do not change anything, you just take the content from any node that is providing it, and you look for the bandwidth, and it's located in Brazil or somewhere around the world, and you don't care, you just pick it. What you could do is to introduce some biasing in the neighbor selection. So you try to cluster the nodes to identify to which regions they belong, to which ISPs they belong, and you give a higher priority to the nodes which have which are located in the same ISP. So you try to keep your connections within the ISP, then the ISP is happy, and you only have very few outgoing links. What I don't understand in this point, because they were always propagating its win-win situation, but I don't see where the peers are winning in this case, so I'm not sure. But in academia and research and in industry, they propagate it always as win-win situation. Okay, latency awareness. So how can you go for the optimizing your connections to the latency? So what you would ideally have, before looking probably at this picture, the ideal state would be if you have your topology where every node is connected to very closely located nodes which have very small delays. So what you want to do basically is to know between every two nodes the delay. But how can you do this in advance before contacting him? And for that you might have this kind of prediction methods. So just from practical reason, at the end you want to have basically the information. If you see any kind of node ID, you want to know which one of them is the best and closest to my location, so which has the lowest delay to my node. And you cannot know this in advance before really contacting him, so that's why you try to predict. And what is done is to use this kind of landmark-based prediction methods. So if this is host 3, and these B nodes are publicly well-known landmark points. That means for them the positioning in the internet and in the geographical position is known, and now host 3 contacts all of them and tries to find out how his delay is. And what you do then, by just contacting them, you can use some triangulation techniques. That means if I know that my delay has let's say this length, then I create then I'm somewhere in this area. So I create a circle about this position with this given distance, and this is where I might be. And if I also have a second point and I also create a circle around it, then I have here a crossing point. I have here a crossing point and over there a crossing point, if you can imagine. And if you create some further nodes and you create also some circles around them, they all match in some specific point. So all of the circles match in one specific point, and so that's why you know somehow your coordinates in a delay space. And if some other nodes try to do the same, so they all come up with the same point basically. So if you have the landmark points, and you know that your delay to a specific node is like this, for example, that's let's say 100 milliseconds, then you might be in this region. And if you know to this node your delay is 170 milliseconds, then you are in this region, and some further regions you come up with, and you find your position, your geographical position in a specific delay space, basically. And by knowing your delay coordinate, so this is some multidimensional number, and by knowing the delay coordinates of the other hosts, you can estimate and calculate your predicted delay to them. So if you know your coordinate and the coordinate of host 2, then you can predict what your delay will be. Okay, so yes, so we still have some time for this topic, and let's discuss the point of net traversal. So net traversal is very important, and so just for example, what is NAT? That stands for Network Address Translation, and the main idea why we need it and why we discuss it is that every node and the nodes must be able to contact each other. So node A must be able to contact node B and node C and otherwise. But we have the problem that with net boxes and firewalls, we have a specific wall which cannot be contacted from outside. And this is quite often occurring. So in real systems, 60 to 80% of the peers are hidden. Just think of your all normal devices that are connected to the internet. Also this notebook and my notebooks at home and everywhere, typically where I am, I don't have a public IP, but I have a private IP, and there's this network translation in place. And what does it mean? So if you are not behind the net, then you have public IPs. Very good. And you can send each other emails or messages, whatever. If you are behind the network translation, then you can also send some messages out, and they can also be answered because there are some holes created for the answers, and that's good. But if somebody from outside wants to contact you, then it doesn't go through, because internally you just have to imagine there's not only node A but also node D, E, F, G, H, any kind of nodes, probably 10, and any message that is directed to the public address of this NAT cannot be assigned to one of these 10 nodes or 20 nodes behind, because you don't know which node should get it. And the same for that other node. Okay, but still, P2P applications need the resources of those PCs, and you need to somehow contact them. So you can, you have to do it. So it's very important. And we will see some techniques how it can be done. So what is NAT again? So why do we have it? Why is it anyway in the internet if it's not good? So it came up with the problem of having sparse IPv4 addresses. So we didn't have enough to cover all the nodes and cover all the pool PCs here, and everybody should have some IP address. For that the IP addresses are not sufficient. So what they did is they introduced this network address translation that everybody can apply at home. And what it does is it rewrites the IP header. So if you send a message from inside your house to the outside, you give your private IP address starting with probably 192, 168 and so on, so this private ID range, and your port, and you give the address of the destination peer, in this case B and 80. The net therefore rewrites both your private IP address to the public one, which is also accessible from the outside, and also rewrites the port. And if the answer comes back, then it's also addressed to the public IP and the port that you gave. And internally it has a mapping table, basically mapping from the external port, external address and the port to your internal address and your internal port. So the port is basically the key to looking up where to which peer and to which node inside to redirect the message to. So very useful, because you might also have very many nodes here and they all communicate with some nodes outside, and the network address translation makes sure that they just use only one public IP, and because you have sufficient ports, you can always map where the message should be dispatched to internally. Yes, so you have the static mapping of the ports in the net device. It's quite popular also with universal plug and play to support these NAT port openings. What kind of features do we also have? Application layer gateways, so you can also open specific ports to forward for specific applications. What you have this connection reversal, so nodes from inside can create some connections, although they are not visible to the internet. You have this relaying, and we will have a look at hole punching, so how we can basically use the NAT to also create some some holes in the network, so that they can be connected from outside. This is the various methods how it can be done. So typically you have a problem if you have two nodes behind so this is the main idea of hole punching. So what I want to say in the beginning, if you would be just alone, you cannot contact each other if you are both behind nuts. You can also not, but what you can do, we will have an example for it, it's probably easier. Okay, so the simplest method to circumvent the NAT is to use a relay that is also used in Skype. If your connection is not going through and you have some problems, then you can use a server which is publicly accessible from outside to send you messages to both of the nodes. So what can be done is basically, if all of the nodes, if both of the nodes contact the server and they just agree, okay, let's create this tunnel and all of the messages from A should be relayed to B. Somehow cleverer is the approach of hole punching. So what you do there is to request a connection to client B over a C, and what it does is server S tells me his public IP and his private IP and sends it back. So I have a server where I can ask for both public IPs and private IPs of the clients. And what I do then is that client A just assumes that it would have an open connection and sends a message. Of course, with this, the message at B is blocked, because you cannot send a message to B without having contacted him before. But what A does also with this step, it creates a hole for a reply. And this can be used by B. Sorry. No. Let me just... Where am I? Yes. So this can be used by B to also send back a reply based on this open hole in the NAT. So what the main idea is in this case is that if you send out a message, then you open a hole in your own NAT, and that can be used by other nodes to establish the connection. And for this UDP hole punching, there are several servers and several libraries also out there that can be used to try to establish with these two steps basically the connection. Yeah. And finally they can connect with each other. Okay. What you should also somehow keep in mind, and what it can be used for, is UDP-NET has the problem that it is closing after a specific lifetime. So it's just just is good for a specific time, so you have to resend all time messages to reopening it all the time. But you can also use it for TCP, which somehow with this socket option SO reuse address that enables it to keep up the connection and to reuse it all the time. But still, so you don't have the guarantees whether it works, because you have different net vendors, different implementations, different approaches of how to do NAT, what is allowed and what is not, and that's why it's just an attempt to do it, but you don't have the guarantee that it really works. And in the worst case, you still have to use the relay. Okay, so I don't want to start this topic today, so thank you very much for your attention. We'll see each other next week. Thanks.